When you put your thumb over the opening of a running garden hose, the water shoots out much faster. Why? It's not magic, but rather it's the law of continuity. So let's derive the law of continuity and the Bernoulli principle, using nothing but a simple box of water. So let's say you have a narrowing tube. Now in here, you have area 1, and here is area 2. Now here, the water flows with velocity 1, and here it flows with velocity 2. So this is an incompressible fluid, like water. It's flowing through this narrowing pipe. Now because water can't be compressed, the amount of water entering the pipe must exactly equal the amount of fluid leaving it. Volume is conserved. So how do we calculate this then? Well, it's really simple. So the volume will be equivalent to area times delta T times V. Now why is this? Well, it's basically base times height. But considering that the height is basically the distance of the water travel, it is V times delta T. Now, on the right side is also the same case. So it will also be equivalent to A2 times V times delta T. Now what does that show? Because V1 must be equal to V2, that means that volume is conserved. So these things cancel out. That means that A1 times V1 is equal to A2 times V2. And that perfectly proves the law of continuity. If the area drops, the velocity must shoot up to keep the volume constant. And that's why garden hose sprays faster. Derive the Bernoulli's principle. So let's recall something. Pressure is force over area. So that means that force is pressure times area. Now let's move on to another term. This term is called rho. Now rho is basically density. So recall that density is mass over volume. That means that rho is also mass over volume. So let's consider this case. Well, Bernoulli's principle can basically be imagined as energy conservation in fluids. So that means that, well, we also have to consider the idea of work. Now what is work again? Work is force times distance, because according to the work energy theorem, the force cancels out and that leaves x. Well, that's up to the later video. So here you have this pipe. Now this pipe has sort of a height difference. That means that in order, when we want to solve these problems, we have to consider energy conservation. So we have already stated that D is equal to velocity times delta T in the previous videos. So that means that work is also here, force times distance. That means that this is equal to pressure times area times velocity times delta T. That means that work is basically pressure times volume. Now let's move on to the real formula derivation. So this is A1, and here you have this A2. And now here you have a delta Y. That means that there's a vertical height difference. Now recall this. Rho is equal to mass over volume. So that means that mass is equal to rho times V. So then we also have to fill this in. So, okay, so it's 1/2 rho V times V1 squared, because of this is 1/2 mv squared. We have to consider the mgh. In this case, that'll be rho VGY1. And then we have to consider the pressure, so that it will be equal to pressure 1 times V, which is V for volume. And that will be equivalent to 1/2 rho VV2 squared plus rho Vg times Y2 plus pressure 2 times volume. Now let's see. Well, the volume is the same, so we can cancel all of these out. So what does this leave us to? Well, if we get all of these cancels out, they'll basically be equivalent to 1/2 rho V1 squared plus rho GY1 plus pressure 1 is equal to 1/2 rho V2 squared plus rho GY2 plus pressure 2. And that's it. Quota era demonstratum. Thank you for watching.